seems to be what's been asked for. Okay, so I'm going to continue talking about mostly minimal surfaces in R3 and mentioning sometimes where the results are also held in three manifolds, and sometimes also when the result holds for constant mean curvature. Okay, so I'm going to, the same subject, same kinds of objects I'm studying. Okay, so this is a slide I had from last time. I just want to make sure that we have a slightly different group each day. So this is one way to define minimal surfaces. In other words, you could take any of these equivalent properties. So our usual property is it has zero mean curvature. Small pieces relative to their boundaries have least area or have least energy or can be realized by approximated physical soap films bounding like a wire. The coordinate functions are harmonic. That's very important for certain properties about minimal surfaces. Certainly properties like understanding Brownian motion on minimal surfaces. So perhaps next week I will talk about the global conformal structure of certain complete minimal surfaces in R3 and properties about area growth. And when I do that, it's very important the coordinate functions are harmonic. Okay? For many global questions, as we saw last time, it's a very useful tool is the Gauss map. And because the second fundamental form is essentially just the derivative of the Gauss map, having trace equal to 0 means that when you you've parameterized this, you can think of parameterizing the surface conformally by the unit disk. Okay, so that means you preserve angles, you preserve orthogonality. You have the Gauss map, which preserves angles. So whenever the second fundamental form is not identically 0, the derivative map actually preserves angles between curves on the surface. They get mapped to curves on the sphere, and the angles are the same. And that's when you take the inward pointing normal to the sphere. So you preserve angles. And the inward pointing normal is because, well, if you do stereographic projection, that's the natural normal vector on the sphere. You pull back of somehow the sphere, the plane is here, and somehow you wrap it around like this. And when you do that, stereographic projection induces an inward pointing normal on the sphere. So that's what we talked about that last time. So at the beginning of this lecture, I'm going to just mention some of these results. We don't have to know how to prove them. I'm just going to mention some of these classical results on sometimes what's referred to as a plateau problem in, say, R3. So in that case, we have a smooth, simple closed curve. For a lot of these problems, that can be a finite collection of simple closed curves. It doesn't necessarily have to be connected. It could be a collection, but just think we'll just do the simple case, simple closed curve. Then we have the result of Allard, which says that there exists a smooth, compact least area surface with the boundary gamma. Okay, what he really shows is there's a surface that somehow homologically glues onto the boundary of the curve. He doesn't really go through and check, for example, that surface has finite topology, like finite genus. But in fact, some other things that he did also, you can prove that there's some boundary regularity. So in fact, when you solve this problem, I'm sure where this is written down, but when you solve this problem, you in fact get a compact least area surface with boundarying the curve. So everything is smooth, okay? What? Yes, it's embedded. It's a Z2. He uses Z2 chains. Z2 chains, and he gets an open surface. It could be a non-orientable surface, right? He's not interested in orientable, not orientable. And so sometimes we are interested in the orientable question. That's more difficult. It's more difficult to get what's called boundary regularity. So a very, very important theorem in the subject is the boundary regularity result of Hart-Simons. So they say you can take, if you have this curve, and I only look at somehow objects, surfaces which are orientable and that somehow have that curve for a boundary, then in fact there are, in some kind of general sense of surface, there's actually a nice compact surface of least area that's orientable that has the curve for a boundary. Okay, so that's nice. In this case, we can say a few more things. We can say that the number of solutions is finite. There are a finite number of these orientable surfaces. In particular, the topology of all examples is bounded. And they only intersect along the curve. So you have a finite number of solutions, and when you have more than one, they only intersect along the boundary curve. Okay. Okey-doke. Okay, so now before these results, we had somehow what's called the classical plateau problem, and that's when we were looking for solutions or mappings of the disk that have the curve for a boundary. So we're looking at really mappings. Let's see that one right there. We're looking for mappings of the disk into R3. We aren't looking, well, this problem we also really weren't looking for embedded surfaces, but it just turns out all the solutions are embedded. So here we're looking at really mappings of the disk into space that have the boundary curve, have the curve as its boundary. Somehow we parameterize the boundary of the disk in the plane parameterizes the curve, and then we have some nice what are called regularity results. So first of all, there exist such mappings. In fact, ones which are what are called least energy. So when you parameterize them conformally, and not only do they have least area, they somehow, in that parameterization, they have least energy. So they're very special, nice. And those special ones, it has some more properties. The first property is that it's proved by Osserman, actually, many years after Douglas and Rideau had solved this. He proved that the surface is in fact an immersion on the open disk. And I think I can remember the proof of this more or less, the idea of the proof. So in general, one has what are called branch points. Remember, the coordinate functions are given by harmonic functions. And then from that, you can kind of see the behavior at a branch point. A branch point is where it's maybe not an immersion. So these least energy mappings could, in principle, have isolated points where the differential was 0. And around those points, they spin, kind of like z to the n, mapping the complex plane to themselves. It kind of some kind of spinning phenomena. And let me see if I can remember. So if we are somehow spinning around a point, this is kind of a picture. A bigger picture. Spinning 2 times around a point, so somehow we're kind of spinning twice around this point. So you have one of these isolated branch points. Let me see if I can remember the proof. So you have the original disk, and we have this sort of picture. You have this sort of self-intersection curve here. Okay, so here's the origin. Think of mapping to this branch point, and somehow we go around here twice. So it kind of looks like z squared. So this arc here matches up with that arc, and it turns out you take this disk. His idea is you take the disk and you cut it open. You cut it open. So in this picture, the immersion goes like this, comes under, and then goes over. Okay? At least the way I've drawn the picture. So it turns out you can just re-glue instead of gluing. In this picture, I glued this to this, and I glue that to that, you can just change how you glue. And so instead of going here up, and then I go down. So he can reorganize the mapping, have the same set in this sort of small picture. He gets the same image set, and he gets a piecewise smooth immersion of a disk. It's no longer smooth along this arc, but it's still piecewise smooth. And then you can lower the energy because there's a crease. You can lower the energy or area along the crease and get a little bit better answer. So if you're looking for least area examples, that contradicts in least area. So sort of a geometric, topological, kind of little geometric argument shows that those classical solutions are immersions. It's not very difficult to do. Sort of reorganizing the mapping is, you don't change the image set, but you change the way it's parameterized. Okay, so that's Osterman's result. And you have a similar idea. It's a little trick here. Similar idea by Gulliver and Leslie. So that's when the curve gamma is analytic. So when a minimal surface has an analytic boundary curve, it always extends past that analytic boundary curve. You can extend the surface analytically across an analytic curve, which means it lies in the interior of a little bit bigger surface. Okay, so a minimal surface, which again might have branch points. These what are called generalized minimal surfaces. So, the question is, can you have branch points on the boundary? Well, if the curve is analytic, in some sense, it lies in the interior. Its branch points occurring in the middle, in the interior of another minimal surface, and then you can kind of, well, being careful, you can check, you can apply Osterman's argument and lower the area a little bit. If it's just smooth, we don't know. Another interesting aspect of this is the result I did with Yao. If the curve has an additional property, so if the curve is what's called extremal, it lies on the boundary of its convex hull. So for example, if you had the round sphere and you took any Jordan curve on it at all, okay, maybe even one that's infinitely long, you take any curve on it at all, you can actually solve Plateau's problem. It bounds a disk of finite area, namely, for example, a disk on its convex hull or a disk on the sphere. So here's your curve gamma. And this solution says, this problem says if it's extremal, then in fact not only is it an immersion, but it's embedded. And probably some people are thinking, why isn't it always embedded? Well, if you take a knot, you take a curve that's knotted, by definition of really being knotted, it does not bound an embedded minimal disk. So you're forced to have intersections in general. But if you're in the boundary of the convex hull, then it turns out that the immersion is always embedded. Okay. For those maybe who know a little bit more about the subject, let me at least show you kind of a simple thing that I originally, when I was thinking about this problem. Suppose you have a Jordan curve on a sphere. Just kind of an idea here. Say a finite length smooth curve on the sphere. Why does it bound at least one embedded minimal disk? Okay, so this is going to be not a complete proof, but for those who understand a little bit more about the subject, you'll get what's going on. So I'm just trying to prove that there's some embedded minimal disk that bounds it. And the idea, this is an idea we're going to talk about later today, if you don't have an embedded disk, I have a branched minimal disk. Okay, so let's even assume the curve is analytic. So I have an immersed disk, right? I have an immersed disk that somehow maybe goes through here and maybe intersects itself, right? So maybe some part of the disk comes through and intersects the disk. This sort of picture like this. But anyway, I can look at the image. So you look at the image of f of d. Solve Plateau's problem, look at f of d. That's some kind of set. And if I take the ball and I remove that set, and then I have a whole bunch of pieces. So in particular, I can look at the piece that has this top disk on it. So remember, the curve gamma is a curve on the two-sphere by the Jordan curve theorem. We have, it bounds two disks, a disk up here and a disk up here on the two-sphere itself. Okay? And if I look at this component, so I take the ball, I remove this, and I take the component delta, which has the disk, say D1, in its boundary, and I take the closure of that component, that's a manifold. This is a manifold with boundary. It's not smooth because in general we have angles. Like the disk comes in here and makes angles and so forth. But the angles are always, say, less than 180 degrees. It's convex looking. Well, this disk on the sphere is convex. The minimal surface, the other parts of the boundary are what are called mean convex. So this boundary is it's like a, think of it like a polyhedron. Kind of looks like a polyhedral domain. We could triangulate it or something. But all the faces are what are called mean convex. Either they're minimal or they are convex themselves, like this disk. We have this disk, and we have these kind of nice corners. So it turns out, on such a manifold, you can, again, solve Plateau's problem. So if I have a curve in that manifold that bounds a mapping of the disk into the manifold, then in fact it bounds, I can solve Plateau's problem in that manifold. This is a very useful idea. You want to not only say, I can solve Plateau's problem in R3, but in some cases I can solve Plateau's problem in a given region of space. So it might not be solving Plateau's problem in R3, might not be the minimum in R3, but it will be the minimum in this domain. And these are what are called good barriers. So this domain, you have to prove, is a good barrier for solving Plateau's problem. But we start having to think beyond R3. All right? We have to start thinking, even here in the case of Riemannian three manifolds. So we have Riemannian three manifolds with good boundaries. Then we can say, when can I solve Plateau's problem in these manifolds? And then you have to go to what's called Maury's solution to the Plateau's problem. So you kind of approach the whole solution a little less classically. But even in this setting, we have to do that. We have to kind of think less classically. We have to think of manifolds with boundary and trying to solve Plateau's problem in those large, somehow in those manifolds. Okay, anyway, you can do the problem. So there's a new immersion, d prime, of least area in this three manifold. Okay? There's something called the isoperimetric inequality. So as long as this curve has a bound on its length, there's a bound on the area of this disk. And this disk is also stable. So they're what are called curvature estimates. We have implied curvature estimates. And okay, so that again might not be embedded. So that maybe I should call that d tilde 1. Okay? But then again, I can do the same problem again. Between d tilde 1 and d1 is another manifold with boundary. And so I can just keep on doing this forever and ever and ever. And I can look at one of these solutions that's closest to this disk. Okay? But because you have curvature estimates and you have area estimates, there'll be, in the end, somehow a disk which is furthest out, somehow closest to that boundary disk on the sphere. And it will have to be embedded, because if it weren't embedded, I could do the whole problem again, and when I solve it, I'll get something even closer to that outside disk, that disk D1 on the boundary sphere. So there's this kind of a general compactness result, which is also a useful idea. There's somehow a disk that's closest. That there's no other somehow minimal surfaces between it and this disk on the sphere. So you have to get some other interesting information. There's somehow a disk is a minimal surface that somehow sits closest to that disk. And it has to be an embedded disk. Okay, so that's another way, at least you have some embedded solutions. Another interesting thing, which I didn't write down here, is similar to the property in the Hart-Simon solution. Okay, in the Hart-Simon solution, we say different solutions. Where's my mouse? Where's the laser thing here? Laser's here. Okay, right here. Different solutions intersect all along gamma. That also is true here. Different solutions only intersect along the boundary. So that's also a nice property. And that turns out to be useful for understanding certain problems in three manifolds. Or, for example, understanding the following problem. So this disjointness problem is closely related to the following topological question. So I didn't think I was going to do this originally, but it's a good idea to do it. So this is a theorem which says the following. So I guess this is with Yao. And this is an interpretation of, what's that theorem? Anyway, it says the following. Take F in the group of diffeomorphisms of R3. Orientation preserving diffeomorphism, that's periodic, finite order. Finite order. Okay, so it's an orientation preserving diffeomorphism of R3 with finite order. Well, inside of this group, we have the subgroup SO3. And we have lots of sort of finite elements in this subgroup. That rotate around a straight line passing through the origin of some rational multiple of pi, or 2 pi. So, for example, you could rotate around a straight line going through the origin. You could rotate by angle 2 pi divided by n. Rotate by 180. That will give us examples of finite order diffeomorphism. So suppose this has order. Okay, wait. The theorem says that this F, that there exists a rotation in SO3, such a finite order, such that F equals G R G inverse, where G is a diffeomorphism of R3. So it says that the way I get all finite order orientation preserving diffeomorphisms of R3 is by conjugating a rotation around a straight line. If you're willing to change coordinates, that's G, every finite order diffeomorphism is linear in those coordinates. Conjugation just means re-looking at the space you're in. So after re-looking at the space I'm in by G, this diffeomorphism, my finite order diffeomorphisms are precisely rotations around a line by some angle. Okay, and you might wonder, why is that the case? So let me just give you a reason as to why that is the case, knowing this property here. Knowing this property that all these immersions are giving you an idea of why this is related to this disjointness property. So let's take a curve on a sphere, okay? And suppose that the curve is invariant under rotation by some angle theta around the z-axis. So suppose the curve has some symmetry. Solve Plateau's problem. Okay? So when I solve Plateau's problem for this curve, okay, here's our curve gamma, which has the symmetry. Okay, we can somehow, it's invariant under rotation by some finite angle. I solve Plateau's problem. This is a solution to the Plateau problem. toe. Okay, we know it's embedded. Okay, but we also know that if we take another solution to it, it's disjoint from it. So if we take this solution and look at r theta of d, well, rotation is an isometry. So this is another solution. Right? It's another solution. But the two solutions, this axis here, links the curve. So the axis intersects the new disk. This is a fixed point. So these two disks, they intersect. This disk and its rotated disk intersect at a point in the interior. But we said if two different solutions, they can't intersect in the interior. So as sets, these have to be the same sets. Not the same mappings, if you think in terms of mappings, but the same sets, which means that I have an equivariant, somehow, theorem. There's these disks, in certain cases, are invariant under isometries of finite order. And somehow this is related to why. It could be a very useful fact. It's related to somehow understanding a completely different question. So these kind of results can become useful tools for studying other problems in three manifolds.
Why did this intersect?
What?
Why did B intersect R theta D?
Okay, so the axis links this curve, so it intersects at least some point. So let's call that point P. Okay, I kind of drew it like it's the origin, but it intersects the point at some point. So that means D intersect R theta D contains in its intersection the point P is in the set of intersection. That means this disk and this disk intersect. So the thing which I said, but it's not written there, is that different solutions intersect only along the boundary curve. So these must not, as sets, they must not be different solutions. They must be the same solution, which means they're the same set. So this least area disk, rotating doesn't change area, it's another least area disk, is the same disk as this one. The disk just rotates inside of itself.
I don't see why R theta B and D intersect that axis the same way.
This curve intersects at some point the disk.
And it intersects R theta D also at another point P.
Okay, it intersects at the point P. But R theta of P equals P. R theta of P equals P. Because that's the axis of rotation. This, I said, rotate around the z-axis. Right, no, okay, so I have this axis of rotation. I assume the curve was invariant under rotation. I want to prove now every least area disk. It might not be unique, but each individual least area disk is invariant under rotation. I'm not claiming that it's unique, but each individual disk is invariant under rotation. And somehow this is related to the fact that finite order orientation preserving diffeomorphisms are obtained by just taking rotations around the line and conjugating by any diffeomorphism. That's exactly how you make all these periodic diffeomorphisms. Okay. All right. So we still have a really interesting question. I think a lot of people, most people that have been in the subject for a long time, at least try to approach this problem one way or another. And that's, we still don't know for this problem here, if you have a smooth boundary curve, if the disk, least area disk is still an immersion. So when you take the classical plateau problem, is it true, take a disk in the plane into R3, least energy, is it true it's an immersion on its boundary or not? So it's a question, right? So we don't know the answer. We only know it when it's analytic. And it's not, when it's analytic, the special, particular kind of least energy mappings are in fact immersions. Okay, so that's a nice question. There's a whole story behind that, like how could you try to prove that, but I'm not going to talk about that. Okay, so from the Gauss map, remember the Gauss map goes to the two-sphere, and we can take its stereographic projection. So let's just backtrack a couple of slides. Right here, right. So if we take this Gauss map, go from, oh, sorry. Where's my map? Oh, pointer. So if we take the Gauss map that goes here to here to here to here, that's called the meromorphic Gauss map, say. I'm not sure. Anyway, lots of times we denote that by little g. So the two-sphere capital G, but the composition usually we denote by little g. So that's what I'm saying is the meromorphic Gauss map. So we're taking the stereographic projection of the Gauss map. And of course, we have in space, we have dx3. We have the differential of x3. It's a harmonic form, and we pull it back. We can pull it back by the mapping. We can think of that as a harmonic one form on the surface. And of course, the function x3 is harmonic, and its differential gives you its conjugate function gives you a related conjugate form. So for people who say a little bit of Hodge theory, so you can think of once you pick a metric, you can think of a one form as just being a vector, right? And if you, by taking inner product with a vector, you get like a one form. So if I just rotate, think of if we're orientable, and I take one, I can just rotate that vector by 90 degrees. Okay? So if I rotate dx3 by 90 degrees, that's called this Hodge star operator, that little star. That gives me another harmonic one form. I multiply by the complex number I. But anyway, it's I times the differential of the conjugate function, conjugate harmonic function. So we have this new form. That's a holomorphic form. Okay, so that's a differential locally of a well-defined holomorphic function. Okay, so that we have a holomorphic form. Then we have this wonderful representation. It says, if I want to recover the surface after translation, so I pick a base point, say think of, I didn't put a base point here, but suppose we had to pick a base point, and at the base point we pass through the origin. Then I can recover the surface by integrating from P naught, the base point, to P along path integrals. I take a path joining those two. I do a path integral. And when I do the path integral, I have three holomorphic forms here. So I do this. This is, again, just some kind of meromorphic function. This is a very simple meromorphic function. And I'm multiplying by dh. So you can really think of dh, put a dh here 3 times if you want. Okay, so we get 3 holomorphic forms, and I can integrate those. And if I get something well-defined after taking real periods, so it has no real periods, in other words, real part of this is well-defined, then I can recover the function. And if I had a function, then it is well-defined. But conversely, if I just kind of wrote this kind of data down, and it was well-defined, in other words, the real part of this is well-defined, there's nothing what's called, no real periods, then conversely, this creates a conformal branched minimal surface. So this is a way of going back and forth. There's a little issue here about being well-defined. If you just try to put anything at all here, in general, there's some indeterminacy. You might have a real period. If you integrate along a different path, you might get a different number, a different real number for a coordinate. So that's the Weierstrass representation. Okay, it's a very useful tool. It tells you how to make all minimal surfaces. And there's a little issue about solving what's called a period problem, but it says if you can solve the period problem, it's well-defined. If it's well-defined, you've already solved the period problem. That's the way you create the surface. Okay, so remember what proper means. So this is this really nice result. It's related to what was called the Clavial problem, which was, are there any complete immersed minimal surfaces in R3 that are bounded? In other words, which lie in a ball. So it turns out there's a nice solution for that for immersions. So for example, you can take any smooth bounded domain. You can take any open surface, can be non-orientable. It can be non-orientable with an uncountable number of ends. Uncountable number of non-orientable ends. You could take a very complicated surface, any surface at all. Then there exists a proper minimal immersion of that surface into this domain, which is smooth and bounded. And in general, we really need smoothness of the domain because Martin and myself, we produced a open domain in the unit ball. Okay, we produced a bounded open domain with the property that but it's not smooth. It's just an open set in R3, such that any complete proper immersion of a surface that has bounded mean curvature, so not just minimal, bounded mean curvature, then there is no such surface that has an annular end. So for example, the plane will not have a complete, proper, or minimal immersion into this particular domain. It will have in the unit ball, but not by this theorem, but it won't have inside of this other domain. So smoothness is very important here.
What does smooth mean?
Smooth means that it has smooth boundary surfaces, finite number of them. So it's a smooth, bounded domain in space. Okay, so let me just give you an idea of how the wire stress representation works here. Okay, so in one of my earlier talks, I had this sort of picture about how do you classify surfaces. So every surface can be somehow, this is more of a picture for orientable, but because I didn't draw everything. It's hard to draw non-orientable things here, but basically you start with a disk. You have this nice exhaustion. You have maybe a pair of pants. Maybe the next stage, when you go to the next stage, you either add a handle or one handle. And here would just be, you haven't really changed the topology. The next stage, maybe I add a handle or maybe I add a pair of pants. And at each stage, I do only one interesting thing. So somehow, if you could imagine taking your favorite surface, I would try to make this complete proper minimal immersion in such a way so that I define it inductively. So I'd first try to make a mapping of this, then a mapping of the next stage, and the next stage, the next stage, each time perturbing a little bit what I made before and somehow trying to get to the boundary of the smooth bounded domain. And I'm not going to really say much about it, but let me just say something about the annulus part. When you try to extend this part somehow, it's like an approximation theorem. So you can have a very wide, somehow you've made something compact before, like in a ball, and then you want to go out here. And so this is some very wild map, but it's controlled in some sense. And the control that we really were after, because we're after another result, the control is that we want when you have different ends of the surface. So if you remember, when you have this kind of representation, each time I add a pair of pants to this representation, I get a new end of the surface. So we want to create, I did the wrong thing. I want to create the immersion. I want to create the immersion so that when I have a pair of pants, I want this to go to a part of the boundary, the smooth boundary of our domain. And I want the limit set of this to be disjoint from the limit set of this. So as I make pair of pants, I want to make sure that this region eventually is disjoint from this image set. The image of this set is going to be disjoint from this set, and they're going to have different limit sets on the boundary of the domain. So there's a lot of control here. You have to worry about a lot of things. Let me just again say, so limit set of distinct ends. So it's a little abstract, but it makes some kind of sense. So I went, after I've done this, I went look at this part somehow goes properly into the boundary, somehow limits to the boundary, and this part limits to the boundary. I want those to be disjoint compact sets in the boundary of the smooth domain in space. So you have to do a lot of control. You have to be careful when you produce your mappings that somehow make something complete. Like, where do they go? That's a little tricky. Okay, but anyway, that's basically the idea. So let me give you these problems. These problems hopefully will be solved, I would hope, in 10 years. So let's just, that's being maybe on the positive side, but great problem. This is maybe the greatest problem in the subject, in my opinion, the classical subject. Okay, so this is not a smooth domain, right? It's like a solid G-hole donut, except I got an infinite number of handles. So the handles in this picture accumulate over here. And they have a certain shape to them. They kind of look funny, a little funny. It's a little fatter here than it is here. Anyway, there's a certain shape, and those shapes allow you to make certain compact minimal surfaces on it, which are related again to our construction that we had before, these proper immersions. Okay, so the surface, okay, let me just go back one more stage here. When you have this simple exhaustion, I put a handle here, but this could be a Mobius strip with a disk removed. So if this is a non-orientable surface, then of course I'm going to have interesting pieces here which are non-orientable. So either I have a genus G, I have a torus with a disk removed, or I have a projective plane with two disks removed. I guess a torus with two disks removed, or a projective plane with two disks removed. So just keep that in mind in that next picture, and then I can answer your question better. So those basic pieces in the simple exhaustion, probably you've seen this picture, some of you have seen this picture before. This is an example of a Mobius strip with a disk removed, or a projective plane with two disks removed. So that's kind of like in the simple exhaustion, that's one of these interesting pieces. Here it is again. Okay, so you see it again, you see it again, you see it again in this picture. So that's somehow a building block to make surfaces. And this is, what is this? This is, this corresponds to, let me see which one. This corresponds to, I guess, an annuals. Corresponds to when you connect things up, you're going to make a pair of pants. This corresponds to when you connect up, you're going to make a torus minus two disks. This is, again, sort of a basic piece in the simple exhaustion. And then you repeat these pieces forever and ever and ever, going off to the right. But somehow I want to connect these up. Well, there's certainly a stable minimal surface that has any topology and is proper. Just by, well, you have to check it. It's not trivial, but a little thought shows you can do something called the bridge theorem. These are stable minimal surfaces. I can connect these up and make any properly embedded minimal surface in this domain. The problem is, what? The solid domain bounded by this, the solid region. See this sort of bluish, kind of like grayish region? That bounded by this infinite genus surface. This is supposed to be a genus G, genus 1, genus 2, genus 3, an infinite genus surface in R3. It's not smooth at one point. So it's smooth except at one point. It's a solid region. So in this region, I can make a properly embedded, stable minimal surface by being very careful, look at a simple decomposition, simple exhaustion, and I have to connect these things up correctly. Using the bridge principle, I can make any open surface properly embedded, in fact, stable in this domain. But it's not complete. The problem is it's not complete. So somehow you have to do something here. You have to do something along this process of connecting things up to make sure that the surface is going to be complete, right. But when we do this, we aren't going to get embedded surfaces in general, okay? So anyway, that's what the picture is. The picture says, what is a necessary and sufficient condition to have a complete, embedded, particular surface? So we fix the surface. So an open surface properly embeds as a complete minimal surface in this particular domain, if and only if every n has infinite genus. So every n representative of an end has infinitely generated fundamental group. That's another way to say it. There are no annular ends on the surface, or no ends of, every end has infinite genus. Okay, so that's the picture. So let me refine this conjecture a little bit. Okay, so let's kind of look at the different things that happen. Usually I don't have enough time to talk about this, but this is a class, so we can look at it a little bit more. Okay, so let's be a little bit more specific about what the conjecture is. There's this bigger conjecture. It says, suppose you have an open surface, and the question is, you want to get, when is it possible that it has a proper, complete, minimal embedding in every smooth bounded domain? So no matter what the smooth bounded domain is, this surface will exist as a properly embedded, complete, properly embedded minimal surface in that domain. So no matter what the domain is, and the condition then is that, the only condition is that it's orientable and every end has infinite genus. So necessary and sufficient condition to always solve this problem for any smooth domain. Now we go to some smooth bounded domain. So we have the important word some. So there exists a smooth bounded domain so that this is a complete, properly embedded, minimal surface in that open domain, which is smooth. And the condition there is that, again, we need every n to have infinite genus, okay? But you can only have a finite number of non-orientable ends. So that's certainly a topological obstruction. So if you take a bounded domain and you have a surface properly embedded in it, which is non-orientable, then it can only have a finite number of non-orientable ends. Okay? Non-orientable ends means that every representative of the end is non-orientable. It's like, okay, so you can certainly make there are surfaces, for example, with an uncountable number of non-orientable ends. So it will certainly, for topological reasons, you cannot put it in a smooth domain in a proper, complete, minimal way. You can't do it in a proper way, forget minimal, okay? And then we have, again, our conjecture we were just talking about. If we don't care about smoothness, then we have this special particular domain that's just sitting there, and every surface somehow is mapping into it as a complete, properly embedded surface as long as every end is complicated. Every end has infinite genus. Okay, so that's somehow more of the complete conjecture. Okay. Harold, do you have a question?
One simple extension to an animal?
What?
How do you do one simple extension to an animal?
Okay, I'll try to. Okay, so think of let's just kind of do it in a ball picture. So suppose your original surface was a ball, and suppose at the end stage you're kind of trying to produce compact surfaces here. Whatever. So inside here I have a finite genus surface, and you say, suppose you had an end which was a simple end of infinite genus. What would I do? Okay, so in my exhaustion, I have an annulus. I think in your exhaustion, you kind of this picture. Suppose my end was simple and had infinite genus. I think that's what you're thinking of. So I could take an annulus, okay? So the strategy here is to take the annulus and make it be somehow close to a region here in the sphere, but it's immersed. So coming out of here, I'm going to get an approximation for the margin is going to be close to this one. And then it's an annulus. It kind of goes back and forth a lot. It goes back and forth a lot to make it be complete. So somehow it goes back and forth very fast, and I get a complete annulus. Okay, and then now I'd like to desingularize this annulus and add an infinite number of handles. That's some. What?
How do you do that staying minimal?
It's hard. You have to do this variation, like it's Ross, what's it called? Deformation, Ross, I forgot what it's Lopez-Ross deformation. You have to define things on the annulus. And you have to create certain meromorphic data that has this property, and yet doesn't change very much what comes previously. And you're going to do this again. And you do this in stages, and then you chop off again. So anyway, so I'm going to talk about that a little bit more in the next slide. All right, so we already know something. You can't, in order to be in a bounded domain, you cannot have an annular n. You have to have infinite topology. And that's a result of Kolding-Minicurso. An annulus, minimal annulus in R3 that's complete embedded with compact boundary, it's like an end of a surface, which is an annulus, is always properly embedded. Okay, so that's a paper they had in Annals like I don't know, 5 years ago or 7 years ago or something. Okay, so we need topological abstraction. You can't do it with annuli. Okay, so here's our approach for doing this. Mostly this is stuff I worked at with Paco Martin a few years ago. And it says that if you can approximate a self-intersecting minimal surface by an embedded compact minimal surface, then you can solve this problem. So you can somehow resolve this issue here. You can keep all the ends away from each other, and you can somehow go to the next stage in this problem. Somehow I can go to my next ball, produce a compact surface, and always in the next deformation, I vary very little what happened before. I got to be careful to make everything complete. I got two issues. I got an issue of making things embedded and being complete at the same time. So that's tricky, but I guess you guys could read this. Maybe I won't go to spend too much time talking about this. But basically, there's a famous question. For example, if you take a catenoid and I intersect it with a compact disk, and so two minimal surfaces intersecting like this with double curves, it turns out I can perturb this picture and make an embedded minimal surface. So I talked about that a little bit the other day, and that was it's a result of Capelleus. Okay? So if you believe that you can do this kind of thing, it's believable you can solve this problem. The problem here is one has triple points. Okay, so one needs to know, for example, take 3 planes in R3. Take the coordinate planes. Okay, so they intersect. Trying too well. Oh well. And you have, of course, the horizontal plane here. Maybe I should draw the axes first. So that might be easier. Okay, so here's x, y, z. And just imagine you have the xy plane, you have the xz plane, and you have the yz plane here. Okay, can I approximate the union of those planes by a properly embedded minimal surface? Approximate in the sense I can find a sequence that does better and better approximations. And then limit, I converge down to the 3 planes. And the answer is you can make these examples. You can look at, you end up with like handles here. So they look like standard way you desingularize 2 planes here, 2 planes here, and somehow it all gets resolved in the center. So one can draw, make, say, for example, this particular surface. But what happens if I tilt the planes a little differently? So it's a big question. Take 3 planes in R3 in general position. Can you find a sequence of minimal surfaces that limits to that particular configuration. It's an open question as well, kind of more almost like a student kind of question. So 3 planes in R3, can you find a family of complete minimal surfaces in R3 that limit to that configuration of 3 planes? That would be a very important step in resolving this problem. If you could do that, you would be in at least good, like you could almost say, I can almost do this problem now. So you'd have to, but try to first do what's called the linearization of the problem, which is 3 planes in R3 in general position, approximated by minimal surfaces, a sequence of minimal surfaces. Okay. All right. So let me talk a little bit more about these embedding problems. They're really basic, important. So one of the first results was this result of Minicurso, complete embedded minimal surface, finite topology is always properly embedded. And then you have this sort of more useful tool. It's because it becomes a tool for doing other things. Kind of go away from finite topology and say, I have any complete connected embedded minimal surface in R3 with positive injectivity radius. Finite topology minimal surfaces always have this property. They're always proper. And this is, the arguments here are based on Minicurso's results, but the point of view is certainly different. It's a different point of view. I'm going to talk a little bit more about that later. Let me just see how I'm doing with time. Okay, got a lot of time, about halfway through. Okay, so we have this very nice result, very important result to remember. In fact, it's very important to realize that this result is even more general. Okay, so this says a complete connected embedded minimal surface of positive injectivity radius in R3 is proper. And it's based on another theorem, I'll state it here, which is very, very useful. So and generalizations of it as well to constant mean curvature. So I can state those, but I'm going to do it in the minimal. So this is Meeks, Rosenberg. Now I'm going to state it a little differently than it's stated in the paper. This is in Duke a few years ago. It says, if you look at a complete minimal surface and a 3-manifold. So this is a 3-manifold. This is complete embedded. Okay. When is the closure of this manifold a minimal lamination? So this is the key step in proving that theorem. Okay, the key step says, okay, this manifold could be anything. It could be a horrible manifold. It doesn't even need to be complete itself. I mean, it's just awful. It could be awful manifold. Just arbitrary manifold, because the property is a local property, and locally manifolds are always good. They're just balls with metrics on them. In fact, balls that are just a little different, the balls are very small, they kind of look like Euclidean space, after homothetically expanding them. So everything's sort of nice. So the condition for the closure to be a minimal lamination, if and only if, if and only if on compact sets, the second fundamental form is bounded. That's certainly clear. The second fundamental form has to be bounded on compact sets. But the condition that somehow we get to get that property is that the injectivity radius function of the surface is bounded. Think of it as an ambient function in N. Okay, so you take an open set or a compact set in N, you can look at this function in that domain in the manifold. So we want this to be is bounded in the ambient space on compact balls. It's just a local property, so you can make the balls small if you want. So in little balls, the injectivity radius function of the surface part of the surface that passes through the ball, its injected radius function is bounded away from 0, okay? Locally bounded away from 0. Away. The problem is when it gets small, away from 0. Okay, so it's strictly it's bigger than some epsilon in any compact set. That as the set changes, that epsilon changes. It's just a local property that you need, and it's not stated. We stated it as a remark, but it turns out for lots of things you do, it's really nice to know that statement. We should have probably stated it in the introduction. So that gives us, it's relatively easy to do that, to show that. Maybe I can almost do that. If I have time today, I'll show how that result there gives this result here. But first, I need something called the half-space theorem. So I'm going to wait a little bit to do that. Okay, so let's, but maybe it'd be worthwhile to see, why is this a corollary of that? Okay, so we'll come back to that question. It's very nice. It's a very nice little proof. Everyone should always, I believe everyone should know. Anyway, so you can then say, well, okay, positive injected radius works, finite topology works. What about finite genus? Maybe I have infinite topology. Okay, so in that situation, we still don't know the answer. Okay, but we do know the answer if you have a countable number of n's. So I don't know if you remember what I drew a picture one of these days of a genus 0 surface with an uncountable number of n's. And I'll just do it with a simple exhaustion kind of picture. Just imagine kind of doing this. Pair of pants, kind of, with a disk. So a pair of pants. Do a pair of pants again. I'll just do them both at the same time. I'll kind of skip some of the stages in the exhaustion. Then another pair of pants. Just keep adding pairs of pants as you go up, like this. That's a genus 0 surface that has no annular ends. Every end has infinite topology. You keep on producing this surface. Every end is very complicated. Even though it has genus 0, it's a planar domain. It's a two-sphere with a Cantor set removed. Okay, so, well, it has an uncountable number of ends. So I don't know if that can occur as a complete embedded minimal surface in R3. I seriously doubt it. Okay, but anyway, we don't know the answer. All right. And, right. But once you know you're properly embedded, there are lots of things you can say. In particular, you can say you have bounded second fundamental form. So you have bounded curvature if you're proper, okay? Somehow, okay. Okay, so here's, again, one of these great conjectures, one of these great problems, one of the really big, outstanding questions. Complete embedded H surface, constant mean curvature in R3, finite genus is proper. So not just for minimal, for any constant mean curvature. And so I haven't really worked on this for about maybe more than about 9 months. But when I was working on this problem last time, I was kind of thinking more about H positive, like H equal 1. In that case, it seems like Giuseppe Tinagli and I could prove, in fact, not only is it proper, it has cubical volume growth. Doesn't mean it has bounded second fundamental form. Generally, you don't have bounded second fundamental form. There are lots of examples of genus 0 without bounded second fundamental form. But you still have this very nice property of having cubical volume growth, cubical area growth. So in balls of radius r, there's a constant for the surface that says the area is no bigger than a constant times r cubed. So you have an estimate on the area growth. That's very interesting. Other question, not just curvature estimates, area estimates. And so when H is positive, it seems like one has nice these area estimates. Okay, so now this is something I put up on the blackboard last lecture, but I decided I would just skip it at that point. So let me talk a little bit more about this theorem. and we're going to be kind of using at least some of the ideas, and we're going to be kind of extrapolating a little bit on aspects of this theorem. So this theorem is also related to these last results I was talking about. And we had special cases. But it's very nice result. Now, I'll just kind of go through here and explain certain things about it. It's a long theorem, but a very useful theorem. Some aspects of it are sort of local. They have a local nature. And the theorem is all about some global things. But one of these sort of local properties is this function delta. Okay, so we have this function delta. And it goes from 0 infinity to 0 infinity. And presumably it's a decreasing function. Okay, presumably decreasing to 0. Okay, so maybe I didn't think about it recently, but I got a feeling it probably goes to 0. I mean, you can't make it. But there exists this nice function, delta, okay, such that, okay, it's a function of, think of the variable being r. So r is going to be somehow a radius, an intrinsic radius on a surface. How far points are away from a base point? So you're on a surface, you can sort of measure how far you're away from a base point, the origin of the surface. Okay? And so if you look at r times delta of r, that product goes to infinity as r goes to infinity. So it has some kind of other property. And then some things hold. Once there's this universal function, and then something holds. Okay? Has some properties, and something holds after that. Okay. For those, okay, so if you are in a manifold, I'm going to state this all for minimal surfaces in R3, but kind of surprisingly is that this statement works for any minimal surface in any homogeneously regular 3 manifold. Okay? It doesn't, okay, when you're homogeneously regular 3 manifold, essentially means in a uniform sense, it's close to Euclidean space at every point. You take a different homogeneously regular 3 manifold, that uniformity can change, but still it's somehow the constants change. What's interesting is this delta function doesn't depend upon those constants. It depends upon the ambient manifold being homogeneously regular, but it's universally defined. It doesn't depend on the constants that give this the ambient space be uniform, so uniform Euclidean. So anyway, but let's just state it, everything in R3. So, okay, so we have a complete embedded minimal surface, and it's got this funny property. It has injectivity radius 0. Okay, so what can we say about the surface? What does it look like? Well, it looks pretty bad around points where the injectivity radius is small. It's got to be topologically interesting. It's got to do something kind of relatively bad. It gets all squinched up. Okay, so that's a bad condition. Okay, so one of the ways you understand bad conditions on surfaces is you expand the scale so the condition becomes nice, like injectivity radius is bigger than or equal to 1. So I talked a little bit about this. So, okay, so here we have the surface M. Here we have our a point. It's going to be, we're going to create points Pn, is that right? Pn here, okay. So these are not going to be points Pn, they're going to be points Qn. We have points some places where the injectivity radius is very small. So think of the injectivity radius at this point as extremely small. Okay? Then in the ball of radius 1, so we have the injectivity radius function at Qn is much, much smaller than 1 over n. It's really, really small. But I restrict myself to the intrinsic ball in M of radius 1. And if you remember, you write down a function f of p equals distance from p to the boundary of this I'll just call it D. I mean, it depends on the point, dqn. dqn divided by the injectivity radius function, I sub m of p, right? You just define this. And you look at points where this function is biggest. And those are going to be somehow these points Pn. So you pick points Pn where this function's maximal. And then I do some rescaling. OK, so that's where these points are coming from. And they satisfy a uniform property. And the uniform property is these points are not on the boundary. This function's 0 on the boundary. So the maximum value doesn't happen at the boundary. There's some positive distance from the boundary. But on the, if the distance here is d of the point Pn to the boundary is d, then on the intrinsic ball of radius d over 2, this intrinsic ball centered at this point, the injectivity radius could be smaller than Pn, the injectivity radius function at Pn, but not much more in the sense that it could be as much as half as big. It could be smaller, but it's not too different. So when I do a homothety of this particular disk, I change my coordinates, or just do a homothety in R3, then when I expand the surface by that same amount, then the injectivity radius on this expanded intrinsic disk is bigger than or equal to half. It's kind of nice. So the function looks nice after expansion. So that's something that's going on here. So we have these points called points of almost minimal injectivity radius. We have numbers which are getting small. So we have the points Pn. So now these points are also like satisfy this role of the Qn. So, but now they're kind of nicer. So we have. So we're going to take the ball. We're going to look at sort of radius epsilon n. These are very, very small numbers centered here. OK, so n times this is still going to 0. OK, and so think of these points as being at the origin. So how do I think of these points as being at the origin? Well, I don't. Again, just put them here. So if I look at the ambient ball, so here's Pn. Radius epsilon n, OK? Inside of here, I can look at the component of the surface that passes through the point Pn. And I've called that Mn. So Mn, so maybe the surface intersects here maybe in a non-compact way, but there's a component that goes through Pn. And part of this property of this component, it has some properties that are related to this delta function. So this component is a compact surface with boundary on the boundary of the ball. So that's nice. It's particularly has finite area. It's a compact surface with boundary on the boundary of the ball. So it's compact. But it also satisfies a chord arc estimate, or a weak chord arc estimate. And that's the second property. So the first part of the statement says its boundaries on the boundary of this ball. It's compact. And this surface is contained in an intrinsic ball. So it's contained. So if you look in the intrinsic ball on the surface, that's an intrinsic that goes outside of here, supposedly. You look at the intrinsic ball of some radius. The radius I pick is R naught. What's R naught in this problem? All right, R naught's right. No, so Rn. I'm not looking at it right. Rn divided by 2, OK? Pn, injectivity radius at Pn, and we have this, this property. OK, so this surface is somehow, all the points in the surface are not too far somehow from the origin. So we're looking at the intrinsic ball here. These points are all inside of a sort of a fixed size intrinsic ball on the surface. And that's the estimate. It gives you an estimate there. And we have this property here as well. Okay? So what that means when you rescale, if I rescale by the injectivity radius function, it turns out, anyway, it's going to turn out that these spheres, their radius, when I multiply epsilon n by the injectivity radius at this point, I'm going to get these balls having radius going to infinity. So, okay, so our scaling factor is going to be this. We can choose everything. We can choose these points Pn. We choose them in a certain way here, but we can be careful about how we choose everything. So that in fact, the injectivity radius function on the scaled surfaces, if we scale these mn surfaces by the injectivity radius function at the point, we aren't too much smaller than 1. Okay, so in fact, so the injectivity radius function is sort of minimal, essentially minimal at the origin, where it's 1, but it could be a little bit smaller. It could be a little bit smaller. It's very close. It's at least kind of like 1. Somehow converging to 1 as we go to infinity. And then we have what happens. Okay, so then you have, after choosing a subsequence, maybe a rotation in R3, we're going to translate these surfaces to the origin. We're going to scale them by the injectivity radius function at the origin. We're only interested in this compact part of the surface. We throw everything else away. So other things might be very interesting in this ambient ball, but we just aren't interested in them for this theorem. We're only focusing our attention on this particular compact part of the surface. So one possibility, well, these translated balls, after scaling, their radius goes to infinity. So maybe integer radiuses going to infinity. And we'd like to say maybe they converge. They're compact minimal surfaces. You know, what can we say about the convergence of these compact minimal surfaces? One possibility is that in compact sets in R3, the norm of the second fundamental form is bounded. You fix any ball in R3, then these compact surfaces, they have bounded second fundamental form in that compact big ball. So fix your favorite big ball. In there, we have bounded second fundamental form. So if you remember so each of these compact surfaces are a lamination, right? They're compact surfaces in an open ball. They have uniformly bounded second fundamental form in that ball, so a subsequence converges to a minimal lamination. That's what happened for geodesic laminations. Remember, a sequence of geodesic laminations converges. We have the same sort of result for minimal surfaces if we have a bound on the second fundamental form. We can do the same argument. So on balls in R3, suppose we have this locally bounded second fundamental form on the sequence. Then we converge to a minimal lamination, but in fact, by using this result with Harold, so you get a limit surface passing through the origin that's complete. Its injectivity radius is, because of this property here, and the way you can do the convergence is nice. The injectivity radius function of the limit surface is going to be bigger and equal to 1 at the origin, and bigger and equal to 1. So by that previous theorem we talked about, it's properly embedded. So so that's one case. One case is no matter how big a ball you pick, the sequence always has bounded second fundamental form in that ball. Each individual compact surface, of course, it has bounded second fundamental form. But maybe there's no uniform bound. Maybe there's a sequence of them, and there's a point in space that accumulates, and in any neighborhood of that point, the norm of the second fundamental form is increasing. Okay. But remember, these surfaces have nice property with their injectivity radius function. So this is the ideal case. Bounded second, no singularities happening at all. Okay. The other possibility is we don't have the previous situation. That means, what does not having the previous situation mean? It means in R3, there's some big ball of some fixed radius r, and there's a point here such that after choosing a subsequence, we have points P1, P2, converging to this point. And the norm of the second fundamental form at these points is going to infinity. That's what the failure of our previous case. So because everything is disks, around these points, what they look like are, in little balls, they look like little helicoids. This follows from the uniqueness of the helicoid. Somehow, in some kind of weak sense, they look like crushed down helicoids that are spinning faster and faster. This is a sequence. So on one surface, I have a little picture like this, here, here, here. And what happens to helicoids is they spin faster and faster and faster. They produce, well, sometimes they produce a foliation. Right? If you homothetically shrink a helicoid, shrink, 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 I produce a foliation of R3 by planes. Well, that's what corresponds to this case. You can converge to a minimal parking garage structure. So it means there's a foliation of R3. So we have a foliation of R3 that passes through this point. Okay, so we have it. So what is the picture? We converge to a foliation of R3. We have places where we don't converge smoothly. Okay, for example, at these points where the norm of the second fundamental form is big, we don't converge smoothly. So we have a bunch of lines, line 1, line 2, line 3. Before we get to the limit, it looks like a spinning helicoids all along here. I'm not sure which way they spin. Everywhere else, I'm converging smoothly to our foliation by planes. This is all after choosing a subsequence. Okay, so that's one possibility. There's a sixth possibility in the next slide, so you've got to keep in mind we haven't exhausted all the possibilities. But this is one possibility. We converge to a minimal parking garage structure. The straight lines appearing in this structure are where we don't converge smoothly to the foliation. We don't converge C1 alpha, or C alpha, I'm sorry. Okay, so you have these lines. Okay, we're going to get a very important property here in a minute. Okay, the distance between the lines is at least 1. So if you look at the distance between the lines, it's at least 1. And the reason for that is you have a helicoid here, you have a helicoid forming here, you have these planar parts here. Well, I can find a curve which goes across here. I go up the axis, sort of the next sheet of the helicoid, and come back across like this. This produces a homotopically non-trivial curve on the surface. And then there's a geodesic. It's a closed geodesic here on the approximating surface. Before I get to the limit, that means I have closed geodesics of some sort of limiting length. But we said the injectivity radius function of the original surfaces, the sequence of surfaces, is like bigger than or equal to 1. So that doesn't permit making these curves of length, geodesics of length 2 plus epsilon. Okay, so the lengths of the curves are related to the distance between the axes. So, all right, so those particular loops are called connection loops. Okay, so let me explain that. It's important as well, connection loops. Important in lots of other problems. So here's our limiting. Suppose we had 2 lines in our parking garage structure. We have something that's very closely approximated to a helicoid here. I'm not sure, maybe it's spinning the same way or not here. Here it's very horizontal. So if you remember, a helicoid really has 2 sheets, right? There's the sort of up sheet and a down sheet. It's like the orientation is up and down. So here there's an up sheet and there's a down sheet coming from the helicoid. and as well over here. So when I do this curve, I go across, okay, to the, and here there's a down sheet, up sheet. I travel along the straight line, like from here to here, like from here up to here. So I come in here, go up here, and go across. Okay, and then down. So that turns out to be a homotopically non-trivial curve. And that's called a connection loop. Loop. And it joins the two axes in the parking garage structure, okay? Well, it turns out, a little thought about the convergence, you can calculate the integral of the conormal. So along this curve, it's very flat here. The curve goes here, here, and across. If you look at the conormal along this curve, so you take the direction vector, the unit tangent vector, you rotate by 90 degrees. Depends on how you rotate, whether you're up or down. You get a vector of length 1 here. And if I integrate that along this curve, that gives me a very interesting vector, which is called the flex vector of that curve. So the integral of the conormal is called the flex vector. All right. All right. So anyway, it turns out that that is non-zero and has a certain length. It's like twice the length, twice the distance between these two axes. Okay, so very important invariant. We get a non-trivial flux on the approximating surfaces. And the last property is also interesting. It says, well, suppose, this is somewhat related to something that Cold and Minicurso do. It says, suppose for every integer, there's a bound on the, for every integer, I should have written one more thing here. You look at these surfaces, intersect them, oops, oh no, it's down here, okay. For all n, there exists a bound on the genus of the surfaces, then it turns out you always are in setting 5. So if you have a bound, if you aren't in setting 4, and you have a bound on the genus of the surfaces, then these surfaces here, then in fact, you always get this parking garage structure. So not bounded second fundamental form, a bound on the genus, then you're good. So these have uniformly bounded genus. I was trying to write down something here, and I guess I wanted to put it here this morning. So, but actually something more interesting is true. So if, let me draw the right answer. Didn't draw it. So if, okay, when you have this parking garage structure, you always have at least 2 columns. Okay? All right? You might have, okay, you have more columns, okay? Okay. Let me see how to say this. Maybe I'll just say it a slightly different way, and we won't worry about columns. Okay. One of 2 things happens when you make a parking garage structure. Either there exists an R naught large so that the genus of the approximating surfaces in this ball, so m lambda n m n minus p n, intersect this ball of radius r in R3. Okay, the ball of radius r in R3. One possibility is that when you go to R naught, is that the component of this surface, which passes through the origin, okay, that component has uniformly bounded genus. Okay? Okay, so one possibility is that some R naught such it doesn't. Either it does or doesn't. So suppose you can find an R naught such, suppose that no matter how big R naught was, you always have a bound on the genus. Or the other possibility is there exists an R naught such you don't have a bound. on the genus of that component. In that case, we always are, and the curvature doesn't stay bounded, we're always in the situation of the parking garage structure. Okay? And even more, what happens is that these domains actually eventually have genus 0. So finite genus actually creates, for n large, genus 0 in big balls. The genus somehow has to disappear from the picture. Yes, Harold? I don't explain that very well. Yeah, let me do that a little bit better. Okay, so case 1. For all n and n, maybe I should put k and n, and you look at the ball of radius k, okay, and you look at the component of mn that goes through here. Remember, mn its boundary is going to be on the ball of radius n. So think of n large, and its boundary is some far away. Look at the component of the surface that goes through the ball of radius k. Suppose that for every k, there's a bound, possibly there's a bound on the genus of this surface. Suppose you have a bound, for each k, you have a bound on the genus. Independent of n. Then this results saying, in fact, eventually you have genus 0, no matter what k was. Or there exists a k, converse of this is case 2, there exists a k such that in that ball you have genus going to infinity. So either you have genus going to infinity in a fixed size ball or not. Now, if you relate that to our property here, so I'm trying to relate all these different things, to this chord arc property, that says something interesting as well. So we get parking garage structures, for example. In fact, parking garage structures in this sort of setting here, as long as we have these points Pn. Look at the failure of this to happen here. Curvature blowing up, so we're blowing up the curvature in a bounded set. The failure of this case to happen means that in an intrinsic ball of some fixed radius, centered at Pn, so an intrinsic ball of radius, say R naught, for some fixed R naught, the genus has to go to infinity. There's no uniform bound.
Is that possible?
I don't know. I'm sure it's possible, yeah. No, okay. How can you do that? Let me try to think. Okay, let me try to draw a picture. We're going to see a picture on the next slide. In the picture, you'll be able to see it. Okay, so this is the second sort of nicest thing to happen. So one is locally bounded second fundamental form. One is, for example, the genus is not going to infinity, or we get these parking garage structures, or we converge to a singular minimal lamination. We're still going to get a limit. We're always getting a limit. So the nice thing about having locally positive injectivity radius is the closure is always some kind of minimal lamination. It just might have singularities. And the singularities are worthwhile analyzing. In R3, it's kind of nicer. It's easier to understand what happens. So this case, we actually have a singular set. So notice I have the singular set of convergence. So I converge outside of a singular set. Singular set's pretty small. I'm not going to say what small means, but it's relatively small. We'll talk about how it's small in a second. For example, sometimes it's countable. Anyway. So we converge to the singular lamination, and it has at least one non-flat leaf. So there's some surface that's in this lamination that's interesting. It's not flat. Remember in the last one, every interesting leaf, somehow we got actually a foliation of R3, right? And we converge smoothly outside of these lines. So in that case, everything is flat. So everything became flat. Here, not everything becomes flat. I should say ahead of time, we don't believe 6 happens. But we don't know. It's a real important question, does it happen? Okay, so then you have the singular set. Okay, you have the lamination converges, the sequence converges outside this small set to a minimal lamination, and it's got some interesting leaf in it. Okay, but things are kind of not good, of course, at the singular set. Things are also kind of not good in terms of convergence on the singular set of convergence. We're not saying that this lamination, you converge smoothly to the lamination. There's somehow this lamination limit, and something converges smoothly outside the singular set of convergence, but we can extend across S of L. So this part right here is bad in terms of convergence, but it's not bad in terms of the structure of the lamination. But these are interesting points. Points where you don't converge smoothly, and points where you can't extend the lamination across. You can't. These are real singularities, okay? You can't extend across. Well, what's interesting is that through each of the points in delta, this sort of bad set, there passes a plane, a flat leaf of the lamination. And on this flat leaf, you might have a countable discrete set of points intersecting delta. But through each point in delta, there passes a plane, a flat leaf. Doesn't mean, so the leaf is the plane minus some points, isolated points. So that's one thing that happens. It's interesting. So we have in it a lamination whose closure, the flat leaves, of course, form a closed set of planes in R3 by definition of lamination. So we have these somehow closed set of planes. Okay, so the closed set, okay, all right. And the other properties, again, we have this failure. There's some big radius so that the intrinsic ball centered at Pn, a fixed intrinsic radius. We have a fixed intrinsic radius, so the genus has to go to infinity. So Harold was asking how would that happen? So I'll try to show a picture of that happening. So as long as the genus stays bounded in for every fixed distance, you fix a distance, you always have bounded genus, then you don't have this structure. The structure doesn't happen. That's not easy to prove, but anyway, that's something that you end up proving. So the genus has to go to infinity at a fixed distance from the point, or you don't have this structure. Okay, all right. In particular, if M has finite genus, you don't have this. Okay, so let me say something a little bit more about this. So we have this collection of planes. Okay, so we have all these. So why are things somehow useful? How do we apply this? Now I have a closed set of planes. So these are somehow the planar leaves, right? I might have a Cantor set of these planar leaves in my picture. But the neat thing about a closed set of planes, what happens if I remove them from the space? So I don't know if you ever thought about that. Take a Cantor set inside the interval 0 to 1. What do you get when you remove it? I get an open set. Well, getting the endpoints. I get an open set of the compact interval. What is an open set? It's a countable collection of open intervals. Right? It's an open set. Everything's second countable. So it's actually, I could make a listing of all those open intervals. The same thing happens for a collection of planes. Remove them from space, I have a countable number of slabs. And those slabs might limit to other things, but what's nice is slabs are slabs. They have two boundary planes. So somewhere we said there was a non-flat leaf. So here's our non-flat leaf inside of a slab. Now on the slab, if you read that thing carefully, you'll notice that these planes. So I could restrict what happens to try to understand another problem. Look at the lamination that we get from one of these slabs, add on the planes, then what do I end up with? I end up with a lamination of a closed slab. And it turns out there are no more planes in here. Remember, through every singular point, there passes a plane. Well, I took one of the slabs, and no more planes in here. I have an interesting leaf somewhere, and be a slab. Could be a half space, but anyway. Okay, and on these planes, I see a countable, discrete set of points separated by distance at least 1, which are coming from the singular set of the original lamination. So, even though the lamination, the singular set might be uncountable, it creates other laminations and regions with interesting leaves which have a countable set of singularities. This is just like a sublamination. And it's nice in the sense that it has a countable number of singularities. And that's related to a slide I showed before, which is the next one. Okay, so this is kind of the picture we have in mind. This, in our setting, this picture doesn't actually happen. So forget that anyway. So nothing, there are no singularities, remember, inside the slab. This is a more general, from a more general result. Okay, so, but we have this sort of, what happens as we come down to one of the planes? So remember, we look like helicoids in our ambient space. The helicoid also went below here, but we see something like a helicoid. Maybe we have another point here with another helicoid, okay, coming down, and it spins an opposite way. So one part of the proof here is you prove that you have to have helicoids that spin two different ways. I'm sorry, spin the same way. So we have to spin, or we have an infinite number. Yeah, we can find two that spin the same way. But if you have two that spin another way, same way, when you go over here, you go up on a connection loop, and you look at the connection loop right above it, you see that those two connection loops intersect in one point, which is a handle. And these handles are limiting down into the plane. And they all lie inside of a ball of fixed radius, right? So remember, we had this property, it's chord arc result. So points are not very far away from, say, this particular point. There's an estimate. If extrinsically, you have an extrinsic estimate in the distance, then action can get to here by a path that's not too far intrinsically. I actually get an estimate from this function delta, this universal function delta. All right, so I don't know if that explains things, but you can imagine you can produce two. You have to find two of these where they spin the same way. Then you look at your connection loops, and these connection loops limit down to the plane, and they all represent handles on the surface, somehow like handles, something like handles. So in this sort of compact part here, where I have another helicoid, in this ball I see infinite genus. You have to have the same spinning. So that's something you have to try to understand. How does spinning influence? Why do you need the same spinning in order to have this kind of problem? But you just have to go through and check things. So if things spin oppositely, then you can only have two. And if you have two, then you're basically in finite genus. Anyway, okay. So this picture was to remind you that we've now reduced not this item 6 to happening, to proving that you can't have something like a lamination of R3 with a countable number of singularities. A minimal lamination of R3 with a countable number of singularities. We can also somehow draw a picture of what those things look like. So we see planes, we see isolated singularities, we see slabs, and we can prove a general result about singular minimal laminations when you only have a countable number of singularities. Okay, and so one of those singularities is, of course, this one. It's a great, maybe almost my favorite problem, actually. Isolated singularity conjecture. So this is one of the great problems in the subject. It motivates a lot of other people's work. So you want to get close to, for example, Harold was interested in some aspect of this problem. It's one of the great motivators. This particular problem is one of the great motivators for other theorems. You say, I want to do this, I'll do a special case. A special case leads me to a wonderful theory about something that controls part of minimal surface theory. So every time you work on this, you come up with a nice new thing. Doesn't solve the problem, but you get a little epsilon closer to solving it. So it says, if I have a properly embedded minimal surface and the complement of a point and a unit ball, so like a compact minimal surface, except it's got a singularity at the origin, that cannot happen. So after many, many years of thinking about the problem, I'm convinced it's true, like 90% convinced. You know, it's like one of those things. I strongly believe it, but I wouldn't be shocked if it wasn't true. But I'd be pretty shocked, but not, you know. Anyway, so this is something that we'd really like to understand. It would, in particular, eliminate these kinds of singularities we have in this picture. Okay. All right, and so there's one good problem, not possible. Let me just tell you a little bit about this problem. Some things are kind of easy to do. One thing you can see is, what is the topology of this open surface? It's got compact boundary on the boundary sphere. It's properly embedded and has the origin there. What can you say about this surface? Well, the way it looks like there, it has infinite genus. So that's something you can say. It has to have infinite genus. Okay? And you have to think about why that is. Well, let's first try to understand, why does it have only one end? In the picture I drew, it only has one end, right? You can't disconnect infinity. Infinity is the point there. You can't disconnect infinity by a compact set. So if you look at the complement, what that means is we take the ball, and we're coming into the singularity. Take any other subball. Okay, so again, you see something coming in. The claim is it only has one non-compact component. Some compact piece, a finite number of compact pieces might come in here, but there's always sort of one compact component left. That means you have one end. The failure of having one end, why can't you have more ends? So let me just try, here's the picture of, you know, maybe something like this. Here's one end. I'll just do like a disconnected surface, right? So somehow if we go further in, I would see this picture if it had more than one end. So somehow a minimal surface here, minimal surface here. Why doesn't that happen? Well, I can take, I'll draw it like I've drawn it. I can imagine a curve here and a curve, the original boundary curve here. They're homologous in this region here by the domain, this surface. So think of, I have a compact surface here. This curve is homologous in this region of space by this subdomain. So in that subdomain, I can solve Plateau's problem. It's a three-manifold with boundary. It's got convex pieces and minimal pieces in its boundary. Okay, there's a little funny thing happening here, which you have to try to figure out how to resolve. But anyway, there's an area minimizing surface that bounds these two, and I can do the same thing over here. I can find a collection of curves here. They're homologous to here, but this is not homologous to 0 in this space by linking. So I can find sequences of stable minimal surfaces that bound the original curves. This sequence of area minimizing surfaces limits to area minimizing surfaces that go through this point. But then you contradict what's called and those surfaces extend across this point. That's related to that removable singularity theorem I mentioned last time. And then you contradict what's called the maximum principle. You can't have two minimal surfaces intersecting at a point, one lying on the other side, one side of the other one. So you can't have more than one end. If you have finite topology, that means when the end has finite genus, If you can't have more than one end, it's an annular end. And then a little thought shows the conformal structure on the annular end is a punctured disk. You have a punctured disk, harmonic functions, well, they extend smoothly across the puncture. And there's your smooth extension. So you have to have infinite genus and one end in order to make a counterexample. All right? Okay, so here's a little bit of explanation as to sort of how to approach the problem. One thing you notice is very nice is any such surface has finite area. That's interesting. So if you have a properly embedded minimal surface in the complement of a point, then playing around with what's called the monotonicity formula, which I'll mention, I was going to mention today, but I don't think I'll get there. No, won't get there today. You can prove that the surface has finite area. And not only that, with respect to diffeomorphisms, it looks like a critical point. So even though it's not compact, it's finite area, you can still do variations through diffeomorphism. It's what's called a varifold, finite mass varifold. And such varifolds have a very interesting property. So we've been doing homothetic expansions, right? We take a surface, we try to understand what happens at a bad point, we homothetically expand, right? We try to understand what's happening at that bad point. Well, at the singular point, you can do the same thing. I can take a sequence of homotheties, okay? And we had finite area, right, on the original surface. Homothetic expansions then produces something that turns out to be cones, flat cones. So flat minimal surface, minimal objects. So let me try to draw a picture. So homothetic expansions give us what are called minimal cones. And minimal cones, for example, we could take geodesic arcs on the sphere, for example, a great circle, another great circle. They don't have to be perpendicular. And you take the cone on these two geodesics, you get something called a minimal cone. So it just means it's a flat surface which is invariant under homotheties. You get a surface invariant under homotheties, and it consists of flat pieces, okay? And then we understand these things pretty well. And dimension 2 is pretty easy to understand. They're made by taking a family of geodesic arcs on the sphere, and they meet at certain kinds of angles. They have certain multiplicities. And then you take a cone on this picture, and you make this flat surface. So we understand, in some sense, if you knew something about the area at the point, somehow you could actually write down all the minimal cones that might arise. However, if you did different homotheties, we only get convergence after choosing subsequences. So maybe you get, in one case, you get two planes intersecting at a point, another which are orthogonal. Another time you get two planes that don't intersect, go through the origin that make a different angle. Okay, so there's this whole question about what is the linear structure at a singularity, and this conjecture says, at least in dimension 3, one has a unique linear structure at the singularity, even if it was immersed. And we can do the immersed version as well. So it means what happens is you come into the singularity, you're seeing this somehow desingularization of a particular cone, like two planes intersecting at a fixed angle. The angle doesn't change. They don't rotate around at different scales. If you come in further in, it always somehow looks like the same thing. It's like a tangent space. The singularity, it's like has a unique tangent space. Okay, so that's a really great problem. And I talked a little bit about this before. So now I'm just going to, I guess we're almost finished for today. That's what time it is. We've got 6 more minutes. So this would be something fairly easy. So we talked about, we had the Weierstrass representation. It's a great way for making minimal surfaces. For example, properly immersed minimal surfaces in a unit ball. We can take an open surface, we can put it into a unit ball as a properly immersed surface. But these examples I'm interested in here are more like properly embedded in R3. So kind of focus, or properly immersed at least. So we have the helicoid. So this is very nice. You can write down this meromorphic function, g of z, e to the iz. You take the very simple, the height differential. It's called the height differential, the dh in the wire stress representation. You just let it be dz in the complex plane. You think of m as being the Riemann surface, which is a complex plane. And that produces, by the wire stress representation, the helicoid. Okay, and we have some nice properties about it. It's minimal by Muessner. It was unique, simply connected, minimal surface in R3. Okay, properly embedded was proved by us, and we just saw Colding and Minicurso prove you're always properly embedded. Simply connected is a plane, finite topology, therefore properly embedded. Properly embedded, we know it's a helicoid. So this is kind of together. Those results give you this nice characterization of the helicoid. Okay, we have the catenoid. Okay, right? Nice representation again. We think as the punctured complex plane. We write down this holomorphic differential. We write down a very simple Gauss map, g of z equals z, and we get the catenoid. Okay. All right. And again, it has some nice properties. It's unique, complete, embedded minimal surface of genus 0, finite topology, and more than one end. Okay. It also is characterized as the unique, complete, embedded minimal surface of finite topology with two ends. So if you take a torus and remove 2 points from it, it doesn't appear as a complete, embedded minimal surface in R3. Because it has, if you remove 2 points from it, it has 2 ends, finite topology. Well, catenoid has genus 0, so it's certainly not going to be the catenoid. So that's very nice as well. And we have, I should have said, Collins' theorem says, if you're properly embedded with finite topology, and you have more than one end, you always have finite total curvature. So that's another very important result here. So properly embedded, finite topology, so finite genus, but at least 2 ends. Then you're always finite total curvature, and then that's the result. We saw this picture before, so there's a little more explanation about what happens in Riemann. We take the catenoid, we shift it a little bit. That's part of a complete minimal surface, kind of expands up to something like this, and we get this very nice surface. Okay, so this is Riemann, and a little thought shows it has a very nice Gauss map. Okay, well this surface is periodic. Let's go back here. Well, I'll just read this part. I'll explain it in a second. Okay, so discovered by Riemann, every horizontal plane intersects in a round circle, straight line, and they're characterized somehow as in terms of genus 0 surface that are proper in R3, infinite topology. Those are the only examples. And in one extreme, they converge to a catenoid, and in the other extreme, they converge to a helicoid. Okay, and here's that sort of nice picture. So I don't think I showed this picture before. Okay, so we're trying to understand what is the topology of Riemann surface. So what we see is in R3 we have, at every height we have a circle. At the height of what's called the planar ends, we have a straight line. Okay, so the circles become a straight line. A straight line is just a point removed from a circle. So here's the parameterization off to the right. So if you remember, we had this nice parameterization of cylinders by flat cylinders. We talked about that last time when we were looking at Schiffman's theorem about convex curve in 2 parallel planes. Every level set was convex. Part of the proof of that was very nice to pick a flat cylinder to parameterize the surface. So Riemann, the same reason, Riemann is parameterized conformally by a flat cylinder such that each circle at a given height parameterizes the intersection with the plane at that height. So we have this very nice parameterization. And a little thought says, at the height of the planar ends, we move a point to make the real number line. And you can just check, you move points on sort of opposite points, opposite opposite sides to get the right conformal structure. Okay. Now, because it has a structure and it's periodic, it's invariant under translation. So if you take a flat cylinder and you translate up, just vertical translation, that makes a flat torus. And a little thought again shows the total curvature of a fundamental domain of this Riemann example covers up the sphere 2 times. Well, on a flat torus, there's a meromorphic function called the Weierstrass P function. So somehow the Gauss map is the Weierstrass P function. And we also have a differential, dz, so on the flat torus, right? So it's not hard to write down the Weierstrass representation. I should have said one more thing, something very interesting that happens for the Riemann family. Remember the Weierstrass representation. You have a Gauss map, and you have a differential. So the two ingredients for G of Z and DH is a holomorphic differential. Okay, we have those two pieces of information. If you multiply this by e to the I theta, you don't change the Gauss map, but you just rotate this holomorphic differential by e to the I theta. Just kind of, anyway, just do that. That produces a new minimal surface. If it's simply connected, it's well-defined. There are no periods if it's simply connected. That's called the associate surface. And it turns out it has the same intrinsic metric. So this gives you, if you take a disk, a minimal disk, you can actually take a minimal disk, make it out of flexible, like plastic, some kind of plastic material. It's fairly hard. But when you do that, you'll notice the plastic is flexible. That's really strange, right? It's kind of like you can take a flat piece of plastic and kind of bend it like a cylinder, right? So if it's a thin piece of plastic, you can bend it. Well, a minimal surface is the same way. You make a little plastic minimal disk, you can twist it. It's flexible. And when you twist it, it still stays minimal. And if you twist it and walk around a little bit to rotate it, you find out its Gauss map doesn't change when you do that. And all you're doing is you're doing this deformation on the surface. Now, if theta equals 90 degrees, pi over 2, that's called the conjugate surface. So somehow that takes the real part of the form to the imaginary goes to minus the real part. It's like multiplying by I. Right? So a very interesting property of the Riemann examples is that they're a conjugate collection of minimal surfaces. So if you take one of them, I can take its conjugate surface. And that conjugate surface is, again, another Riemann surface. It looks very different, but it's another Riemann example. And there's one special one which goes to itself under this transformation. Okay, this is related to the fact that the catenoid and the helicoid are conjugate minimal surfaces. If I take a little piece of the catenoid, the helicoid, and I can make it out of plastic, and I twist it, I make a little part of the helicoid. I got to twist it by 90 degrees. I twist it all the way around. It just matches up with a part of the helicoid. We get this nice local isometric deformations. Anyway, we have this sort of very interesting property of that. Okay, again, this is somehow the same picture. We see this parameterization. Now, we want to compactify the cylinder. So we're still trying to understand the topology of Riemann. We can see it's parameterized by a cylinder. But what is a cylinder conformally? An infinite cylinder conformally is just the unit sphere with the north and south pole removed. That's the conformal structure of an infinite cylinder. Okay, and remember we moved all these points. We moved all these points on the cylinder, right? So those just are they just limit to the north and south pole. So the top of the end of the cylinder is the north pole, the bottom end is the south pole, and now we understand exactly the topology of Riemann. we take a discrete set of points out of the sphere, except for the north and south pole aren't discrete, which limit to the north and south pole, and then we remove the north and south pole. So we have exactly 2 limit points, and those, therefore, we have the unique minimal genus 0 minimal surface, which has 2 limit ends. So Riemann has 2 limit ends. The limit ends corresponding to the north and south pole. Limit ends are just limit points of those points you remove. So we understand the topology pretty well. Okay, and there was that picture before. We kind of looked at this again. As you go through the family that goes to helicoid limits, if you do the right homotheta, you actually converge to a parking garage structure. Okay, so now I guess that's probably it for today. I think I probably. So after this, I'm going to do some elementary things. I'm going to talk about the interior maximum principle. I'm going to use it to do certain things, and quote some of these nice theorems. Talk a little bit about the Jacobi operator, and so just some other kind of classical results. So that's where I'm going next time.